Yeah. So let us start with lecture 3 where we left. I was trying to introduce a simple example. Oh, before that, there was a question regarding Hamilton-Jacobi equations, no? That was a PD. Hmm? Yes?
Existence, how to show the
Yeah.
exist.
Yeah, the Hamilton-Jacobi equations in particular, its connection to optimal control problems, everything is very well discussed in Ivan's book, PDE, Introduction to PDE. He does it initially in, I think, chapter 3, and again later on in nonlinear PDE chapter. In the first chapter, he talks about the existence, connection, and all that. In the towards the end, he also talks about viscosity solutions, and so that may be a place where you can find under what conditions we can get existence. Hmm? So this is a good reference I can think of. Okay. And there are also many books on HJB equations on that title alone. So there is a lot of literature. So at least this may be a starting point, Evan's book. Okay, so I was looking at the simple finite dimensional example. Instead of Laplacian of y equal to f, I have replaced it by ay equal to bu, so that a is a matrix, b is another matrix, u is the control, y is the state. So we want to minimize the functional jyu, for example, y minus yd square plus lambda u square, etc. So the idea is, which is the same we will follow in elliptic as well as parabolic equation, is when you have j is as a function of y and u, I would like to write y as a function of u. Y and u are related to each other through the equation. The equation was ay equal to bu. In the PDE case, it will be some PDE elliptic or parabolic. So if I manage to write the solution operator S is equal to A inverse B, in this case, I know how to find the derivative. So my condition will be just to compute the derivative of f of u, which now is involving s of u. So that means I have to do a chain rule. F prime of u will give me it is like quadratic functional su minus yd square. So that derivative will give me s transpose acting on su minus yd. So that will be the derivative. So here you have to recall multivariable calculus, how to differentiate a quadratic function in Rn. And lambda u square will give me 2 lambda u. The 2.5 have disappeared. So they cancel each other. So this is the derivative which I can calculate easily. So optimality conditions now can be written in this theorem. If u bar is a solution to the minimization problem, jyu, u is in some convex set admissible controls, and the matrix equation ay equal to bu. Now, u bar is the optimal control if and only if it satisfies a variational inequality. The inequality appears because you are in a convex subset. Suppose you are in the whole space U, which is the easiest case to understand, and if U is the whole space U, then the derivative itself will be zero, because I can take instead of U minus U bar everything, every other vector, and so I can conclude F prime U bar is itself is zero. So this we'll keep it in mind. This is the thing which will keep coming even in non-linear spaces. Okay. So let me go to the optimality system in our case, which will look very similar in the PDE case also. So in this finite dimensional example, suppose I want to minimize f of u to be half of SU minus YD, just a minute. So, SU minus YD square plus lambda U square. This condition is, what is the condition? F prime U acting on U minus U bar is greater than or equal to 0. So that will become, I have substituted what is the derivative that we computed here. So we computed here F prime U. That F prime U is S transpose acting on SU minus YD and plus lambda U. So that is what I have to substitute here. So this acting on U minus U bar is always greater than, so this variational inequality is satisfied. If U is the whole space, which is the easiest case for us to understand, if U bar is an optimal control with optimal state Y bar, then I can write down the adjoint state P and as well as U bar. U bar will be precisely exactly equal to 1 upon lambda B transpose P bar, and AY will be so AY will be, I can plug it BU instead of U. I have substituted whatever U bar I found out, and that will become minus 1 by lambda B transpose P bar. And the adjoint equation is, you see the adjoint of A appears here. A transpose P is equal to Y minus YD. This is because I'm going to define P in this way. In the solution operator, we had this. So that is how the adjoint equation appears. So the original equation AY with where I have substituted for U bar, and the adjoint equation AT, A transpose P. So this is the optimality system, which we will keep encountering even in the PDE case. So we have to keep this in mind as a prototype. Okay. So let us take up the PDE optimal control. And yeah, there are some questions.
One is this lambda can be seen as Lagrange multiplier?
Where is
The earlier.
No, the lambda is just a constant that we put to make the problem more amenable to solution. So it is a constant, sorry, it's not a Lagrange multiplier, but I have added it as a particularly as a constant, which will help me to converge faster, hopefully. So that is so it's not a Lagrange multiplier here. Okay. Yeah. Anything else?
That is all.
Okay. Okay. So what is the plan for PDE optimal control problem? Let us see. So first we have to worry about well-postness of the PDE. That when what about existence, uniqueness, etc. Then that will help me to write the solution Y as a function of the control U. And we have to clarify from which space to which space it goes, because now we are dealing with all function spaces. So that is the tricky part in this technical part in this well-postness of the PD. Then we have to worry about existence of an optimal control, and which usually under convexity assumptions and inversion of the A, if our A is operator A is invertible, then we may be able to prove the existence. And then I have to worry about necessary or sufficient optimality conditions and adjoint equation. We have to define the adjoint vector suitably. And finally, how to compute the optimal control. Okay, so let us start with the Dirichlet problem. I suppose everyone remembers what is Laplacian. Laplacian of Y stands for, so minus Laplacian of Y is summation d2y by dxi square. I runs from 1 to n. So this is the usual notation we follow for writing this elliptic operator Laplacian. Okay. Now the Dirichlet boundary condition y equal to 0 on gamma. So we have to worry about the solution of the PD. Usually it is easier to prove the weak solution. And weak solution means I have to go to a suitable Sobolev space. And if you are familiar with the Sobolev space, H1 0, 0 represents the y vanishes on the boundary of the domain gamma. So H1 is the function is in L2 and its derivative is weak derivative is also in L2. So this is the analog of C1 functions, but in the L2 setup. So these are all Hilbert spaces. This is the suitable Sobolev space in which we can pose the problem and get the weak solutions. So what is the way you will pose the problem? Instead of pointwise, it is going to be tested with the test functions on integrated out. So the integral over omega of grad u dot grad phi is equal to f phi. And this is precisely what you will get if y is a classical C2 solution. And if you integrate it by with phi, then integration by parts will give you precisely this equation. Because the boundary term will vanish because y is 0 on the boundary. So for a classical solution, this is what is necessarily satisfied. So but to define a weak solution, you see in this, if y is in L2 or gradient y is in L2 is enough to define this way. If this is satisfied for every test function phi coming from H10 of omega, then we will call it a weak solution. Now, this is very amenable to Lax-Milgram theory. So we will take V to be H10 of omega, a bilinear form. That means it's linear in each of these arguments. It has two arguments, U and V. And A of UV is equal to gradient U dot gradient V. And probably this is all familiar to you, then you don't bother. If it is totally new, then also you don't bother. We'll accept there is a weak solution. Okay. I'm just recalling what is the way you will show a weak solution. Define the continuous linear functional on V is f of V is the right-hand side acting on f, right-hand side of the weak formulation. Now, a Lax-Milgram theorem can be applied. I have a Hilbert space and A is a continuous V elliptic bilinear form. Continuous means the modulus of the AUV is bounded by the norms of U and V in the V norms, and elliptic means AUV is bounded below also. AUU is bounded below by, sorry, I have written V, this should be U. Okay, AUU is greater than or equal to beta naught U square. Now, for every f in V star, the equation A, Y, V is equal to FV admits a unique solution, which also satisfies this continuity. That is, given F, you have a solution, and the solution norm is dominated by the right-hand side norm. So this is a very useful to get the existence and uniqueness and existence and continuity estimate. So this will give me, let us translate it in our function space. What does it mean? This is the abstract Lax-Milgram theorem, which is like Riesz representation theorem in a Hilbert space. So if you have omega is a Lipschitz domain, then for every f in L2 of omega, remember f is the right-hand side, then the Dirichlet problem has a unique weak solution satisfying for some constant C positive independent of F, that Y norm in H10 is bounded by the right-hand side norm in L2. So this is what the now existence and uniqueness part is taken care of. So now we will go back to optimal stationary heat problem. So I want to look at the minus Laplacian of y equal to beta u. So it is heated in the interior, I'm assuming. So the control is applied in the interior, maybe in a small subset or in the whole domain. And y is 0 on gamma, which I can interpret as the domain omega is insulated for heat. So there is no heat transfer at the boundary. And I have to minimize the j, which is the y minus yd square integrated over omega plus lambda by 2 integral u square integrated over omega. Now u is defined in the interior of omega. That is why I have taken integral over omega square. Now, we can also assume the control to be bounded between UA and UB. Now, with the constraints, if UA is minus infinity, UB is plus infinity, will correspond to the whole space. That is, U can be any function in L2 of omega. So when I write these inequalities, we have to interpret it as almost everywhere X in omega. Okay. So because these are all just L2 functions, so I have to be careful, or you can interpret it, you can say even continuous control if it is allowed. So our first step, as we did in the finite dimensional example, I have to write the J as a function of U. So I have to write Y as a function of U. So for that, what we are going to do is, first we will define a map G of U to be Y of U. So given the control U, our U is sitting in the right hand side. So I can define the solution Y of U. It is exactly like the solution operator. I can imagine this to be minus Laplacian of inverse of minus Laplacian with Dirichlet boundary condition. Now, G is a continuous linear operator, and that is what the existence theorem also confirmed. And now if, see, but this is going from L2 to H1, I have to bring it to H1 to L2. So H1 0 is embedded in L2 of omega. So I have to remember that. So I can simply take E to be the identity operator from H1 or H1 0 to L2 of omega. So if I combine all this, I get my solution operator, which will go from L2 to L2. So earlier I had S from Rm to Rm or Rn to Rn, so it was easier. But now these are function spaces. I have to carefully write down it goes from where to where. But anyway, I can write finally S of U to be Y of U. So I can write the solution Y as a function of U. So if I plug it into the abstract framework, I have a function capital F, F of U, to be minimized over all U in a set of admissible controls. What is that? Half of SU minus YD square plus lambda by 2 U square. So now the right hand side is completely a function of U. And this may be easier for us to find the derivative and write the optimality condition. Okay, U add is the set of admissible controls in the control space U. Remember, this capital U is going to be some Hilbert space now. So we can write down the theorem. If let U and H be real Hilbert spaces and U add be a non-empty closed convex subset of U. Now, if YD belongs to H and lambda greater than or equal to 0, that is lambda is the parameter I'm adding before the control cost. And S be a continuous linear operator from U to H, then the optimization problem has a solution. So the solution is assured in this case. And if lambda is positive, or if S is injective, then the optimization problem has a unique solution. So that is the use of lambda here. It will help me to get the unique solution in some situations. Okay, so existence is taken care of. Now I have to worry about the derivative. So for that, I have to recall the differentiability in non-linear spaces. So maybe you are familiar with Frechet derivatives, or it is the same as total derivative in Rn, whatever definition you used, I recall here. If at U in capital U, if there is a linear operator capital A from U to H such that f of U plus H is given by, it's something like a Taylor's approach, f of U plus a linear operator acting on H plus a remainder term, whereas the remainder term should satisfy this estimate that limit as norm H goes to 0, the norm of RUH by norm H should be 0. If this happens, then capital F is Frechet differentiable at U, and the Frechet derivative of capital F is precisely the linear operator A. Okay, and so that is the definition we will be using. Now that we are equipped with the notion of derivative in a non-linear space, we can write down the optimality condition exactly like what we did in the finite dimensional situation. So let U be a real Hilbert space and U add be non-empty closed convex subset of U, and let F be differentiable in an open set containing the U add set of controls. If U bar is a solution to the minimization problem, minimum of f of U, where U belongs to U add, then it solves the variational inequality. Exactly like what I wrote down in the case of finite dimensional example a little before in this lecture. F prime U acting on U minus U bar is greater than or equal to 0 for all U in U add. Except that we have to interpret it differently. F prime U bar is now a linear operator, the Frechet derivative of the function capital F. So that will act on some vectors in U add, and then that will give me a number. So whereas in the finite dimensional example, both were Rm vectors, so I could write the Rm scalar product, and that gave me the number, and we concluded it is greater than or equal to 0. As before, if U add happens to be the whole space capital U, then I can conclude the derivative itself is 0. The inequality becomes equality here. So that is the easier case where we can completely characterize the U bar, exactly calculate. Okay. Conversely, if U bar in U add solves the variational inequality and F is convex, then U bar is a solution to the minimization problem. So this is what both necessary and sufficient conditions, with we call it the optimality conditions. So let me go to our particular example. I want to know what is the derivative. What is the how to compute the derivative. So if I write down for f of u to be half of su minus yd square plus lambda by 2 norm u square. Now the question is how to compute the derivative of f. I need f prime evaluated at u bar. So u bar is a solution to the quadratic minimization problem if and only if u bar is a solution to the variational inequality. Why we wrote this is because this is precisely f prime at u bar. This we had calculated earlier in the case of finite dimensional Euclidean space. It will be exactly similar, except the interpretations will be different. Now S star is no more a matrix, but it's an operator from a Hilbert space to another Hilbert space. S star is the adjoint of S. So if S was going from U to capital H, S star will go from capital H to U. So that is the adjoint. And the adjoints will always satisfy this equality. We have to recall this. This is the same in finite dimension also when you have matrices. So the inner product between V and SU in H, SU will be a vector in H, okay, because S was going from U to H. Now this number will be equal to S star of V comma U, where S star will be going from H to U. So S star of V will be a vector in U. So that vector and this U, there will be an inner product in U, because both are Hilbert spaces, and so that is the thing I have to remember. So we have characterized the solution here, I mean the optimality condition, but I have to still calculate S star. How do we do that? That is what is the next thing, because our equation is given in terms of Laplacian. I have to find out what is S star in terms of the given equation. Now, in this situation, what comes to our rescue is a Green's formula. What is Green's formula? If you have the equation minus Laplacian of y plus c naught y equal to beta u, and an adjoint equation for that, that is minus Laplacian of p plus c naught p equal to z, both satisfy zero boundary conditions, then I have a result saying z, the right hand side of the adjoint equation multiplied by y is precisely beta u multiplied by the adjoint vector p. How do we get this? The proof is very simple. What you have to do is you take any one of the equation, multiply by the other. For example, let me take the equation for y. Suppose you multiply by p, I will have on the right hand side beta pu. That is what I want on the right hand side in the answer. But the left hand side has so many terms that will have to be eliminated using the adjoint equation satisfied by p. So how do we do that? The standard integration by parts. So first term will be minus Laplacian of y into p. So you have to throw the Laplacian on p. So you will have to integrate by parts twice, and both the times boundary terms will disappear. So I will end up with minus Laplacian of y into p will be precisely minus Laplacian of p into y, and c naught yp is the same. So, but this I know from the equation that will be z. So that will give me zy. So this Green's formula is very simple in the case of Laplace equation, but it could be complicated when I go to heat equation, because there will be time variable and space variable. Here there is only one variable, x. Okay, but this is not enough. I have to calculate the S star. Okay, that is the so I have to calculate the S star of the something I needed. What is S star? That is what I want. So for the equation minus Laplacian of y equal to beta u with y equal to 0 on the boundary, and for S from L2 to L2 given by S equal to Eg, the adjoint operator here, it will be precisely the adjoint operator S star will go from S star L2 to L2 is given by S star of Z is beta P, and the beta is whatever is on the right hand side, and P will satisfy. Now what you want is the argument that you put on the right hand side. The same philosophy will repeat. Of course, I can compute it from this in this equation what I showed you. U SU equal to V SU is same as S star VU. So that will also help you to compute. That is what is precisely the Green's formula will be useful. So what I have, what we have found out, of course, to check is S star of Z will be beta P, where P solves the adjoint equation with Z as the right hand side. This is what we have to remember now. Now I can write down the derivative of which is appearing in the optimality conditions. So U bar is an optimal control with the optimal state Y bar and the adjoint state P. Then they satisfy this variational inequality. Beta P plus lambda U bar acting on V minus U bar is greater than or equal to 0. Now, why did we get this? Because this is precisely the derivative that is computed. What is the derivative? I recall to you the derivative was S star acting on SU minus YD. S star, I told you what is the S star we computed here. S star was like this. I have to evaluate it on, I needed S star acting on SU bar, I forget what was that, SU bar minus YD. YD was the, yeah, this is what is the derivative. So this is the derivative which is computed here, and that will give me precisely the P equation for P. So the equation for P will be precisely, you remember, if S star of whatever is this, I have to put it on the right hand side for the P equation. What is SU bar? SU bar is nothing but Y bar. So this will be Y bar minus YD. So S star of Y bar minus YD, if I write down, I have to write down minus Laplacian of P. The right hand side will be whatever argument you are looking at. So that is why I have taken the adjoint equation as Y minus YD. So the adjoint equation will satisfy minus Laplacian of P is equal to Y minus YD, and the original equation was given as minus Laplacian of Y equal to beta U. Both have Dirichlet boundary condition, and this beta P plus lambda U bar is the derivative of this function, and that will be acting on V minus U bar will be greater than or equal to 0. The easier case, I hope I have written, okay, let me, if it is 0, then I can even calculate what is U. The U will be beta P by minus beta P by lambda. Okay, so the minimum principle will be, if the adjoint, if lambda is strictly positive, then I can write the optimal control U bar and the optimal adjoint state P through this minimum principle, like we wrote in the case of Pontryagin minimum principle. So that will be, if you write this whole thing, beta P V lambda by 2 V square, and you allow V to take values between UA and UB, then that minimum will be attained exactly at the U bar, the optimal control U bar. So you could give a projection formula in this case. What is U bar? U bar will be given by this, but this expression. If UA is minus infinity and UB is plus infinity, that is no control constraints, then everywhere U bar will be precisely this will be the optimal control. PAB otherwise will be the projection. The projection is defined in this range. So let us not worry about this constraints. Suppose there is no control constraint, that is much easier to solve. Then my control space is the whole of L2 omega, and then I can write exactly the same equation 1 by lambda beta P. And the optimality system, I can write, you substitute for beta U as, there is something wrong. I think I made a mistake. It should be, yeah, minus 1 by lambda beta into, maybe this should be P, I think. Yeah, because I have substituted for U. So this should be P, I think, but I'm not sure. It could be a typo. Minus Laplacian of P equal to Y minus Y omega. This is what I calculated in the adjoint system. So it is similar to the ODE case. I get a coupled differential equation and it's adjoint. One is for the state vector, one is for the adjoint vector. So these two coupled elliptic system will have to be solved. And if I can find P, then I can find the optimal control. So the way we can solve the problem is, one is you try to solve these two together coupled, and then you calculate the optimal control. Of course, numerically, because by hand it's going to be more difficult. Okay, so let me go to the other case, the boundary control. So here we are trying to put the control over the boundary, yeah, alpha y minus u minus y, which is lambda by 2 gradient u square, and u is L2 of gamma now. The domain is the boundary. And again, I have to see what is the solution operator. Now it is going from L2 gamma to H1 omega. So what we will do is, I can take it to, from the trace to the H1 of omega, I'll take GU equal to Y of U. So that is once again from E into G. Okay, so composition of these two operators. Again, I have to compute the derivative and via the adjoint vector. So I'll just indicate what is the optimality system. So here it is the boundary conditions, whatever you put as Neumann boundary conditions, a similar Neumann boundary condition appears for P, whereas the right hand side is Y minus YD, that is the same as before. Then it is alpha P plus lambda U, V minus U is greater than or equal to 0. And if it is the control is unconstrained, or it is the whole L2 of gamma, then I can write U bar X is precisely, this is the vector. So you can write down the solution. So let me give the references. L.C. Evans' mathematical optimal control theory. He doesn't do PDE control, so that's a separate one. No, these two are not useful. The next one is Fleming and Rischel is deterministic and stochastic optimal control. The initial part, he quickly recalls deterministic control. J.L. Lyon's optimal control of systems governed by PDEs was 1971, which kick-started the subject. It's a classic. After that, Donald Kirk, of course, this is for ODE rather, not for PDE. Jean-Pierre Rameau, yeah, the PDE books are these two and J.L. Lyon's. And of course, Fleming and Rischel. Okay, the others are more on the ODE side. My treatment is following Freddie Troelsch, Optimal Control of PDE, Theory, Methods and Applications. It's a AMS volume 112. He spends a lot of time how to numerically solve these things, how to solve this coupled given system and the adjoint system simultaneously. And Jean-Pierre Rameau also, this Ficus course notes, excellent source for optimal control of PDEs, where he tackles not only elliptic, also parabolic and other types, and semilinear. Same with Freddie Troelsch. The second chapter is on elliptic, third chapter on linear parabolic. After that, he takes up semilinear problems and he extends the theory to that also. Okay, any questions now? It's time for
Yes.
question.
Huh.
Yes.
So what is n in del y by del n before this?
Sorry?
Uh, yeah.
Here?
Yes, del y by del n.
Yeah, this is the normal derivative. This is the normal derivative. Or if you have a boundary and this is n bar is the outward normal, we take the normal in that direction. In the simple one-dimensional case, it will be just the derivative. Otherwise, if you are in a curve, two-dimensional curve, you have either tangential derivative or normal derivative. So d by dn is the normal derivative. Yeah.
That is the only question.
Okay, okay. So then we quickly move on to the last one, which is parabolic. It's more technical, so I may not finish everything, but I'll just indicate how the treatment runs parallel. That is enough to understand the idea. Okay. So this is, it's again, we want to see what is a typical optimal control of parabolic PDE, a heat equation. Now it is no more stationary, but it's evolving. So time is also involved. So how does an optimal control problem arise, and what all the study method you will do? First, well postness we will study, and I'm not going to do because that is more technical than the elliptic case, and then the existence of optimal control, and then optimality conditions. We could jump to optimality conditions, but here again the spaces will be a little technical. So I need to give some time to introduce the spaces. Okay, but let us see an example first. Suppose a room has to be cooled. No, today it's very cold here already. Let me say the room is to be heated to a certain desired temperature profile before a meeting starts at time t. We could either use an air cooler inside the room or an air conditioner fixed on the window. So if your air cooler is inside the room, it will correspond to the interior control. And if your air conditioner fixed on the window, it will correspond to the boundary control. What is our aim? We want to choose the cooling or the control suitably so that the room has the desired temperature profile at time t, when the time t your meeting starts or whatever. Okay, so this is a problem. So let us try to model this problem mathematically. So for a given desired profile yd of x is given. That is your desired profile you want to reach in time t. So my functional is j of yu is like before, half of y of x, time is fixed as capital T, yd of x, because I want the solution to reach the profile yd of x. So everything is now a function of x. We take the L2 norm over omega. Then again, as before, lambda is useful for existence and uniqueness. So I keep a lambda by 2. Now the control is interior control, then or boundary control. If it is boundary control, I'm going to take the integral over d omega and 0 to t uxt. So what is the equation satisfied? This is the heat equation. Yt stands for dy by dt, the partial derivative with respect to time, minus Laplacian of y is 0. I denote Q to be the product space omega cross 0t. Y is typically a function of x comma t, where x comes from omega, t comes from 0t. And this dy by dn is the normal derivative. So the normal derivative is usually given prescribed. So that is given to be alpha times u minus y. So we are controlling via u on the boundary. And we want to minimize the distance between our solution and the desired profile at time t, plus also the control cost. With alpha and lambda greater than 0, and the condition on the control u is the u lies between ua and ub for all xt in the boundary. So this is our model. Like before, I have a functional, except that the functional now depends on x and t. The functions depend on x and t. And the equation is an time evolving parabolic type equation. And the control is applied on the boundary. So we will follow the same procedure like before. I would like to write j to be just a function of u. So I have to write y as a function of the control, if possible. And I have to understand from which space to which space and how to differentiate. There will be a solution operator S, and I have to calculate the adjoint of S. That will give me adjoint of this equation. Here the adjoint will be will have to be calculated very carefully, because there is a first order derivative which will give me a minus sign, and initial value problem adjoint will go to terminal value problem. So these are the slight points which we have to keep in mind. Okay, so I recall as before the finite dimensional example, what I did was y is equal to A inverse of BU. Then my solution operator is A inverse of BU. So my existence will give me the A inverse. The solution operator can be composed with whatever B is given. Then my derivative will be S transpose SU minus YD plus lambda U. We have to calculate the adjoint S transpose in this case of infinite dimensional operator. So this is the theorem which I recall. So for the PDE optimal control, the plan will be first, as usual, well-postness. And then we finished in elliptic case, we used Lax-Milgram theorem. And in the parabolic equation, usually Galerkin approximation is useful. So I will just recall, let us not worry too much about the technical details. And then we go to existence and necessary optimality conditions. So motivation for time-dependent Sobolev spaces. Now what happens is, earlier I had only one variable, so I took h10 of omega. But I have two variables, x in omega, t in 0t. And the solution may have different regularity in different variables. So I cannot think, it may not be very optimal to work with L2 of omega cross 0t, but we would like to separate the variables and discuss the regularity in each variable separately, because the regularity of the solution in the variables x and t may not be same, because t only one derivative is appearing. In x there are two derivatives appearing. So for example, if I take, I will classical solutions, I'll demand C1 in time, C2 in space. So the same way, when I go to the weak solutions, I have to think of Sobolev spaces which will separate out the two variables. So that is the technical point here. And that will bring us to time-dependent Sobolev spaces. So I have to view for each t, the element yt to be a vector in the function space h1 of omega. So you see already it has different integrability condition in time and in space. So LP of 0tx, I'll be always using only L2 of 0tx, but anyway, LP can be defined for at least 1 to infinity. For infinity, will have to be defined differently. So here I'll take measurable functions, and 0 to t, the LP norm over X is bounded. Here X could be any space. In particular, I'm going to take H1 omega. Similarly, I can take any Banach space or any Hilbert space I can take. So what I would like to do is I'll take X to be H1 omega or H1 0 of omega. So then I can demand in time variable, it may be just LP or it may be continuous. So this is the time dependent spaces. Now I will go to weak solution of the heat equation. Like we did for the Laplace equation, I am going to integrate with the test function and then interpret the integral identity. Okay. So let y naught belong to L2 of omega. So f is given the right hand side, which is now L2 of 0 t L2 omega. What does it mean? For each t between 0 to t, I have it associates an element from L2 of omega. So this is a simpler one, but the next one is L2 of 0, solution will lie in L2 of 0 t H1 0 of omega. So what does it mean? For each t, my solution yt as a function of x will be an element of H1 0 of omega. And what about the time derivative yt? That will be for each t, it will be an element of h minus 1 of omega. Who is h minus 1? It is the dual space of h1 0 of omega. These are not needed, but just in case you want to later on pick it up, this will help. This is a weak solution of the problem. Now I have taken zero boundary condition, and this is for just for simplicity. If y satisfies for every phi in h1 0 of omega, so I have also the time derivative. Now yt, d by dt of yt into phi, this is the inner product in h1 0 of omega. Remember, h1 0 is a Hilbert space. So this is the inner product in that Hilbert space. The next one is what we can guess. It was similar in the elliptic case. Gradient y of t. Remember, y also depends on t. So this happens for every t, but these are all only L2 functions. So I have to say almost everywhere in t. And I have put the condition y at time t equal to 0 will be y dot. Dot will y0 dot represents the function in it's a function on omega, because y naught is coming from L2 of omega. But the question is why the trace is defined, why y0 is defined. That is one question. The y0 is defined, that is because you usually have a trace theory. If you have some regularity for the derivative, then you can expect the trace at a point t equal to 0 to be defined. So if y is in L2 h1 0, yt, the time derivative is in L2 h minus 1, then your function y becomes a continuous function of time taking values in L2 of omega. So this will help me to define what is the value of y of 0, and that will be an element of L2 of 0. So this initial condition makes sense as an element of L2 of omega. Now I just accept the well-posedness of the LPDE because this is a standard theorem you may find in Evans, for example. So the heat equation with this kind of forcing term, it has a solution, and you have these estimates for a constant C, which is this gives me a solution operator. This is what I need to define the S. The idea of the proof is the Galerkin approximation yn, and then you have to pass to the limit. So I skip this. Existence of optimal control. If U and H are Hilbert spaces, and U add is a non-empty closed bounded convex subset of U, And yd is a given vector in the Hilbert space H, and lambda is some parameter greater than or equal to 0. And S is some operator, continuous linear operator from U to H. Then this functional F, this is our functional. We have written the solution Y as a function SU. This admits an optimal solution U bar. Further, if lambda is positive and S is injective, then the solution is also unique. You may get unique optimal control in this case. So as I said, convexity helps in all these things. Okay, let me come to optimality condition in the remaining 5 minutes. So I look at the cost functional for any u in L2 of sigma y in W0t. So I have to define the operator, yes, solution operator. We want to write y as a function of u. So that is what is explained here, but it is too technical for me to go into the detail. So GU, I want to write y of u. So G is bounded. It takes, given a function in L2 of sigma, it takes it to the solution in W0t. W0t, remember, it was a function of functions depending on time and space. And from there, I have to bring it to L2 of omega. How do? We restrict it by taking the trace at time t equal to capital T, and that is the operator E. So thus the continuous linear mapping, it can go from L2 sigma to L2 omega. Finally, I have got my S, and so the derivative can be calculated. And that will involve, as before, S star acting on SU minus YD. So the same expression keeps coming again and again. It boils down to the calculation of the adjoint S star. So if the Frechet derivative of the first part is this, S star into SU minus YD. If Frechet derivative of the second part is lambda times UV. And so the necessary condition will be F prime U tilde, or the optimal control, it will be greater than or equal to 0. So that helps me to, that brings me now to the crucial adjoint problem. What is the adjoint equation in the case of the heat equation? I can just give that and then stop maybe, because we can't really go through the calculations. Again, it will be through the adjoint problem and a Green's formula. You have to multiply the original equation by the adjoint vector, etc. I need to find out S star using the relation SU, inner product between SU and V is U acting on S star V. So remember, if SU equal to WT, what does it mean? W solves the given PDE with the right hand side, the boundary condition as alpha U, and Wx0 initial condition as 0. So that is the meaning of SU equal to W. Now I'll take the adjoint equation. I have to get a Green's formula, right? So I write the adjoint equation. I just guess that, or if you don't guess, you have to write it as Z and calculate and then arrive at what you want. But here we know, we have done it several times. So I just guessed Px capital T must be the derivative of, with respect to y, of the cost functional. That was y bar y tilde minus yd. So that I put it as the terminal condition for P adjoint problem. The boundary condition will be the Neumann with 0 Neumann boundary condition. And now if you multiply W equation with P and integrate by parts, you have to remember, you have to throw the d by dt on W to P. That will give me minus Pt. And when you do Laplacian of W, throw it on Laplace to P, you will have to integrate twice by parts. That will give me minus Laplacian of P. And you have to tackle all the boundary terms And finally, hopefully, I'll arrive at the Green's formula. W act into P is precisely alpha P into U. You can guess alpha P into U in the boundary which will remain, and W into P will also be remaining. Okay. So this will tell me finally how to compute S star acting on SU tilde minus YD. And so that will be alpha P acting on U minus U bar. So this is what we were trying to find out. And then I write down the theorem. If U tilde is the optimal control, then P is the adjoint state, and then U tilde is the optimal control. If and only if, this is what we were wondering, alpha P plus lambda U bar, because here I computed only F1 prime, because I knew F2 prime was lambda U tilde. So you put together everything multiplied by U minus U. This must, if it is the whole space, I will get alpha P plus lambda U tilde is 0. That will give me exactly the optimal control. So a control associated with the state Y tilde is optimal if and only if, this is if I have a projection, if this kind of minimum principle we have, if lambda is strictly positive, then I can project it between UA minus UB to this for a given, so if it is UA is minus infinity, UB is plus infinity, which corresponds to no control constraint, then I will get the U bar is exactly minus 1 by lambda alpha P. So I can compute this, but we have to solve, remember, we have to solve the adjoint problem. Adjoint problem and the given original problem, both will have to be solved. So this was the boundary control. So in the remaining 2 minutes, I can just indicate the interior control. So the interior control, the original equation, you are putting beta U on the right hand side, and you put the Neumann boundary condition, zero Neumann, homogeneous Neumann boundary condition on the boundary. Now the question is, what should be the adjoint problem, or what is the optimal control? So again, you can have control constraints and optimality conditions. So again, you can write down, you can guess, this is the derivative of the control cost with respect to Y. That will give me Y tilde minus YD. And the Dirichlet boundary condition, or the terminal condition Px capital T is 0. And the derivative will be, in this case, beta P plus lambda U bar. Beta P we calculated like before earlier. It is the same what we calculated in the case of boundary control, similar to that, except that now the integral will be over Q, that is omega cross 0t. Now minimum principle can be written down, and the optimal control will be minus 1 by lambda beta P, and that brings me to the end of the lecture. So the PDE books are Leon's, as I mentioned, optimal control of systems governed by PDEs in 1971. Donald Kirk is more for ODE, but I'll say Jean-Pierre Rameau for optimal control of PDEs, which is the Ficus course notes. It still exists in the Ficus website probably. Freddie Troelsch is the optimal control of PDEs, theory, methods, and application. My slides are very much based on Troelsch book, so you may be able to find all the details, in particular the Green's formula and the calculations in Troelsch book. Okay.
On the behalf of Indian Women in Mathematics, IWM, and the organizers from University of Hyderabad, I would like to express our sincere gratitude to all of you for attending this insightful mini course on optimization and optimal control theory. We are deeply embedded to our esteemed speaker, Professor Mythily Ramaswamy, for graciously accepting our invitation and delivering such a captivating lectures. Her expertise and engaging presentation styles have undoubtedly enriched the learning experience for all participants. We would like to extend our heartfelt thanks to National Board for Higher Mathematics, NBHM, and the Committee for Women in Mathematics, CWM, for their generous support and funding of this mini course. We are immensely grateful to Professor Riddhi Shah, the chairperson of IWM, for her invaluable guidance and encouragement throughout the event. We also thank Professor Anisa for her meticulously introduction about IWM activity and also other panelists for their presence during the lecture. As usual, Vinayak has lent his technical support efficiently. I would like to thank him. Lastly, we would like to acknowledge the enthusiastic participation of all the attendees, and we thank each and everyone who attended the talk and asked interesting questions that contribute to the success of this mini course. We are excited to announce our next and final mini course for this academic year to be delivered by Professor Tanvi Jain in January 2025. So please stay tuned to IWM website for further updates. Thank you all again.
Yeah, thank you very much. It's a very good initiative by IWM to give these mini courses, and it is really helpful to the students. And I'm happy that it helped me to organize the thoughts in. I never thought about it before, so it's really helpful.